In the vast expanse of our solar system, far beyond the familiar planets like Earth and Mars lies Neptune, a giant shrouded in a mesmerizing blue hue. This distant world, often overlooked, holds many secrets waiting to be uncovered. Orbiting this ice giant is a fascinating collection of moons, each with its own unique story to tell. These moons, varying in size and characteristics, form a captivating dance around Neptune, adding to the planet's mystique. Among them is Sao, a small faint moon that was discovered on August 14, 2002. Despite its diminutive size, Sao has captured the interest of astronomers and space enthusiasts alike. A dedicated team of astronomers led by Matthew J. Holman used powerful telescopes to spot this distant world. Their meticulous observations and relentless pursuit of knowledge led to the identification of Sao, adding another piece to the cosmic puzzle. Sao's name originates from Greek mythology, where Sao is one of the Nereids, sea nymphs known for their beauty and grace. These mythological figures were believed to inhabit the depths of the ocean, embodying the mysteries of the sea. Just as the Nereids were linked to the sea, Sao, the moon, is bound to Neptune, the Roman god of the sea. This celestial connection between mythology and astronomy adds a poetic layer to our understanding of the cosmos. The discovery of Sao marked a significant moment in our exploration of the outer solar system. It was a testament to human curiosity and the relentless drive to explore the unknown. Each new discovery like Sao brings us closer to understanding the intricate processes that led to the formation of our solar system. These findings help us piece together the history of our cosmic neighborhood, revealing the dynamic and ever-changing nature of space. Sao serves as a reminder that there is still much to learn about our solar system and the vast universe beyond. Every new moon, planet, or celestial body we discover opens up new possibilities and questions, driving us to continue our journey of exploration and discovery. Sao's journey around Neptune is far from ordinary. Unlike most moons, which orbit their planets in a relatively circular manner, Sao charts a more rebellious path. Its orbit is highly eccentric, meaning its distance from Neptune varies significantly. One of the most intriguing aspects of Sao's orbit is its retrograde motion. Imagine a racetrack where most objects are speeding along in one direction, and then there's Sao, moving against the flow. This retrograde motion suggests that Sao may have been captured by Neptune's gravity long ago. Sao's rebellious dance around Neptune provides a glimpse into this turbulent past. Each new piece of data brings us closer to unraveling the mysteries of Sao's rebellious dance and the secrets it holds about the formation and evolution of our solar system. Peering across the vast cosmic gulf, it is difficult to discern the precise details of Sao's physical characteristics. However, based on observations, astronomers have gleaned some insights into this distant moon. Sao is estimated to be quite small, with a diameter of roughly 44 kilometers. The surface of Sao is likely composed of a mixture of ices and rock. The dominant ice is believed to be water ice, potentially mixed with other volatile compounds. While Sao's small size and extreme distance from the Sun make it an unlikely candidate for life, its composition provides valuable insights into the distribution of water and other volatiles in the early solar system. Understanding the composition and distribution of these building blocks of life is crucial in our quest to unravel the origins of life on Earth. Further observations and potentially even future missions to Sao could reveal more about its surface composition and internal structure. Sao is not alone in its peculiar dance around Neptune. It belongs to a group of moons known as irregular satellites, characterized by their distant, eccentric, and often inclined orbits. These irregular moons stand in stark contrast to the regular satellites like Neptune's largest moon, Triton. Neptune's irregular moon system is a diverse collection of objects, each with its own unique story. Some of these moons, like Sao, exhibit retrograde motion, suggesting a capture origin. The study of these irregular moons provides a window into the dynamic and often violent processes that shape the outer solar system. The irregular moons of Neptune can be grouped into different dynamical families based on similarities in their orbital characteristics. By studying these families, scientists can piece together the history of Neptune's moon system. Understanding the dynamics of these past events is essential for comprehending the current state of our solar system. The unusual characteristics of Sao's orbit have led astronomers to favor the capture scenario as the most likely explanation for its origin. Sao's orbit is highly inclined and eccentric, which is not typical for moons that formed in place around their parent planets. Unlike regular moons, captured moons are believed to have originated elsewhere in the solar system. These moons are thought to have been wandering through space before being ensnared by the gravitational pull of a planet. The capture process is a complex and chaotic dance governed by the laws of gravity. It involves intricate interactions where the gravitational forces of a planet can alter the trajectory of a passing object, pulling it into orbit. One possible scenario for Sao's capture involves a close encounter between the early Neptune and a passing object from the Kuiper Belt. The Kuiper Belt is a region of the solar system beyond Neptune, filled with icy bodies and remnants from the solar system's formation. During this encounter, gravitational forces could have slowed down the passing object, allowing Neptune to capture it. This process would require a delicate balance of forces, where the object's speed and direction are just right for capture. The captured object's original momentum would have been transferred into its new orbit. This transfer of momentum is a key aspect of the capture process, determining the final orbit of the captured moon. Multiple capture events could have occurred in Neptune's early history, leading to the diverse collection of irregular moons we see today. Each capture event would have added a new moon with its own unique orbit and characteristics. The capture scenario for Sao's origin is further supported by its physical characteristics, similar to objects found in the Kuiper Belt. These similarities suggest that Sao may have originated in this distant region before being captured by Neptune. While the details of Sao's capture remain shrouded in mystery, its unusual orbital characteristics provide compelling evidence for its extra-Neptunian origins. The study of Sao and other irregular moons continues to offer valuable insights into the dynamic processes that shaped our solar system. Sao's retrograde motion, orbiting Neptune in the opposite direction to the planet's rotation, is a captivating characteristic. This counterintuitive movement is a telltale sign of the moon's turbulent past. In the well-ordered ballet of our solar system, most planets and their moons orbit the sun in the same direction as the sun's rotation. However, captured moons like Sao often defy this norm, exhibiting retrograde motion as a consequence of their capture event. Imagine a cosmic game of billiards where Neptune acts as the cue ball and Sao represents one of the colored balls. When Neptune encountered Sao, the gravitational interaction could have resulted in Sao being pulled into an orbit opposite to Neptune's spin. Retrograde motion is not unique to Sao. Several other irregular moons in our solar system also exhibit this peculiar characteristic. By analyzing the orbital characteristics of these celestial rebels, astronomers can piece together the history of our solar system. Adding another layer of intrigue to Sao's already unusual orbit is its high inclination. This inclination is not just a minor tilt, it is a significant deviation from the norm. While most regular moons orbit their planets in roughly the same plane as their planet's equator, Sao's orbital plane is tilted at a significant angle. This means that instead of following the usual path, Sao takes a more complex and inclined route around Neptune. This tilted trajectory, like its retrograde motion, points towards a past shaped by gravitational interactions and capture events. These events likely involved other celestial bodies exerting forces that altered Sao's original path, leading to its current high-inclination orbit. Imagine a flat disk representing the plane of Neptune's equator, and its regular moons orbiting within this plane. This disk is a simplified model of how most moons behave, staying close to the equatorial plane. Sao, with its high inclination, would be like a marble rolling around the rim of a tilted bowl. This metaphor helps visualize how Sao's orbit is not aligned with the typical equatorial plane, but rather takes a more elevated and angled path. The high inclination of Sao's orbit suggests that the captured moon originated from a region of space significantly different from the plane of Neptune's equator. This region could have been far from Neptune, where gravitational forces from other bodies were stronger. This further supports the theory that Sao was captured from the Kuiper Belt, a region of icy bodies with a wide range of orbital inclinations. The Kuiper Belt is known for its diverse and scattered objects, many of which have orbits that are highly inclined compared to the planets. By analyzing the orbital inclinations of captured moons like Sao, astronomers can gain insights into the structure and evolution of the Kuiper Belt. These studies help us understand not only the history of these distant objects but also the dynamic processes that govern our solar system. Despite its discovery over 2 decades ago, Sao remains a relatively unexplored world. Its small size, faintness, and extreme distance from Earth make it a challenging target for observation and study. However, advancements in telescope technology and the development of new space missions offer tantalizing possibilities for future exploration. One promising avenue for future exploration is the development of more powerful ground-based and space-based telescopes. These next-generation instruments will be equipped with advanced optics and imaging techniques, allowing astronomers to study Sao in greater detail. Another exciting possibility is the development of a dedicated mission to the ice giant systems, similar to the Cassini-Huygens mission. A dedicated spacecraft could perform close flybys of Sao, capturing high-resolution images and analyzing its composition. The data gathered from future observations and potential missions to Sao would enhance our understanding of this particular moon. The exploration of Sao and other distant worlds is a testament to human curiosity and our innate desire to explore the unknown.